Design Lab, Experiment number 2, Porter Governor. Aim to study the relation of performance characteristics of Porter Governor. Also to study the force versus radius of rotation, relation between force and radius of rotation, relation between speed and sleeve displacement, govern effort and governor power. Procedure: arrange the governor mechanism under test as per required configuration. This can be done by fitting chosen sleeve weights as per required configuration. Connect the motor to the speed control unit or thermostat. Measure down the initial radius of rotation, length of the link, initial height of the governor. Increase the speed gradually using thermostat provided. Center sleeve rises until the center sleeve rises to the lowest and aligns with the first division on the graduated scale. Record the sleeve's position and speed. Increase the speed gradually to have suitable sleeve movements and note down the sleeve displacement and speed accordingly throughout the range of sleeve. Calculate the value of stability, sensitiveness of governor. Plot the governor characteristics curves using tabular data. Precautions: increase the speed gradually. Take the sleeve displacement when the pointer is steady. Ensure the load on the sleeve does not hit the upper sleeve of the governor. Bring the demurst to the zero position. So this is a Porter Governor. So Porter Governor has a central mass loaded on the governor with the empty sleeve. So balls are connected to the governor with the help of arms or links. So observation: length of each link is 125. Initial height of the governor H0 is 93 mm. Initial radius of rotation R0 is 136.5. Weight of each ball assembly is 0.75 kg. Weight of the empty sliding sleeve is 1.72 kg. Also note down maximum equilibrium speed N2 and minimum equilibrium speed N1, and also the maximum sleeve displacement X max. Now draw a tabular column as shown in the figure with the sleeve lift, speed, height H, alpha, angle of inclination alpha, and radius of rotation R, force F, effort Q, and power P. So formulas are as follows. So angular velocity omega is 2 pi n by 60 to convert the speed of governor into angular velocity. The instantaneous height for displacement h is h0 minus x by 2, where h0 is initial, x is the displacements of the sleeves. Third is angular of inclination alpha is cos inverse of h by l. Then fourth is instantaneous radius of rotation R is 50 plus L sin alpha. Then fifth is controlling force F is M plus capital M into omega square R upon 1000. Governor effort Q is C into M plus mg, where C is change of speed N2 minus N1 by N. We get it from the formula. Then governor power P is Q into X max, maximum displacement. And then last is sensitiveness of the governor N2 minus N1 minus N2 plus N1 by 2. Now on the same setup, so we have increased for the Porter Governor, we increased the load. So we have provided additional load on the empty sleeve. So this additional load is 1.5 kg. So this makes the Porter Governor. So and now the working of the Porter Governor. Now slowly increase the speed until the sleeve begins to rise. And note down the minimum equilibrium speed N1. So until the sleeve begins to rise, for the small movement, note down the minimum equilibrium speed N1. Now it has increased. Increased slowly. For the small movement, note down the governor speed. So this value divided by 2 is governor speed. So this is 363 divided by 2 is the governor speed. So that is minimum equilibrium speed. Now increase the thermostat slowly till we get the maximum displacement. So maximum displacement here is 70 mm. For this X max, this is X max, maximum displacement 70 mm. So X max for at 70 mm, the speed is so for the speed is 521 divided 520 518 521 divided by 2 is the maximum equilibrium speed n2. Note down the maximum equilibrium speed n2. So note down the maximum, minimum and maximum equilibrium speed n1 and n2s, and also the maximum displacement x max. Now for 10 mm rise, for the 10 mm displacement, note down the speed. So this is divided by 2, so 374 divided by 2. So we get, so for 10 mm rise, note down the speed. Similarly, for 20 mm rise, for the 20 mm rise, note down the speed. So from here, this is motor speed, so divided by 2 we get the governor speed. So this is motor speed 300 divided by 2. So for 20 mm rise, note down the governor speed. So divided by 2, motor speed divided by 2, we get governor speed. Similarly for 30 mm rise, note down the motor speed. So motor speed is 430 divided by 2. So we get it as for motor speed for 30 mm divided by 2, we get the governor speed. Similarly for 40 mm rise, note down the motor speed. Note down the motor speed and divide this by 441 by 2. So we get for 40 mm rise divided by 2, we get the governor speed. Similarly for 50 mm, rise, note down the governor speed. This is motor speed divided by 2, we get governor speed 462 by 2. So we get the for 50 mm displacement, we get the governor speed. So after this, stop the machine. Now calculation. So calculation, first is angular velocity omega is 2 pi n by 60. So for the first reading, 2 pi n, that is governor speed, that is 206 by 60. Note down the angular speed is 21.5 radians per second. Then second formula, instantaneous height h is h naught minus x by 2. So h is h naught minus x by 2, that is h naught is, which is initial height of governor at 93, minus x is displacement 10 by 2, we get 88. Similarly for all the readings, apply the formula and get the h of all the readings. Tabulate all the omega also. Now alpha is cos inverse h minus h by L. So cos inverse h is the instantaneous height for first reading is 88 upon L is the length of the arm 125. So we get alpha is 45.25 degrees. Similarly calculate for all readings, calculate the alpha. Now radius of rotation r is 50 plus L sin alpha. So r is 50 plus L sin alpha, 50 plus L is 125, sin alpha is just the found value. So similarly calculate the radius of rotation for all the readings with the same formula. Next, the controlling force F is m plus m omega square r by 1000. So here there are 3 loads. So here there are 3 loads. Mass of the ball 0.5 kg and mass of the center sleeve and 1.5 kg additional loads, that is 3.22 kg into omega square into r by 1000. So we get the force. Similarly calculate the force of all the readings. Next is governor effort. Q is C into m plus mg into g. So C is n2 minus n1 by n. So maximum equilibrium speed minus minimum equilibrium speed upon n. We get the C. Substitute m plus m into g is 9.81. So we get the governor effort. So m is the weight of the ball. Capital M is mass of the whole mass of the sleeve, and additional weight 3.22 kg. Total is 3.22 kg into 9.81. We get the Q. Governor effort Q. Then governor power P is Q into x max, maximum displacement. So governor power, that is into x max 90 mm you get the governor power. Lastly, sensitiveness. Formula is n2 minus n1 upon n2 plus n1 by 2. Substituting the maximum and minimum equilibrium speeds n2 and minus n1, n2 plus n1 by 2 into 2, we get the sensitiveness. Similarly, tabulate all the values for all the readings and plot a graph of speed on y-axis and displacement on the x-axis, and plot all the points. Also, one more graph of force on the y-axis and radius of rotation on the x-axis. So plot the graph. And lastly, write the result. Governor effect of the porter governor is governor effect of the governor power of the porter governor and sensitiveness of the porter governor.